All right, I'm back. So the next thing I want to tell you about is I'm going to talk a little bit about automating GlusterFS at Facebook, sort of the approaches we use, the issues we encounter, and how we solve them. And I'm going to tell it to you in the context of what we think of as the life cycle of a Gluster volume. So very briefly, we categorize the stages or life cycle of a Gluster volume into sort of three main pieces. The first is the creation phase, where we have to take hardware and assemble it into a Gluster volume so that a customer can read and write data. After the creation process is done, we sort of enter maintenance mode, or what I heard earlier as day 2 mode, which primarily involves software upgrades and hardware repairs. And this is sort of what I think of as the steady state of the volume. And then finally, we come to the decommission stage. And in this particular instance, I'm not talking about decommissioning the volume. I'm talking about decommissioning the hardware behind the volume. So the volume will live on, the data will live on, the traffic will live on, but we will need to replace the hardware at some point. So the very first step of the creation process is the validation of hardware. So at Facebook, we explicitly want to run on homogeneous hardware for a single Gluster volume. What I mean by this is we want all of the bricks in the volume to be the exact same size. We want the CPU and memory configurations to be the exact same. At a very high level, this basically ensures that problems are easy to debug for our team. When we log on to any host in a Gluster volume, we know at some level that these hosts are all identical, and we can make certain assumptions when we're debugging problems. Or in other words, we can eliminate a certain class of problems when all of the hardware is exactly the same. The next sort of most important step in the creation process is what I call layout management. So our automation to create a Gluster volume, we call it Ant Farm. And it runs through the regular flow of creating a Gluster volume. It runs peer probe, it issues Gluster vol create through the CLI. But perhaps the most important thing it does is specify a very specific order of bricks. And the order that we specify, the way we do it is we want our replicas to be placed across multiple racks. The reason for this is, we have two reasons for this. One is we want to be resilient to rack switches failing. We also want to be resilient. We also need to be able to do maintenance on these rack switches. So it's sort of a prerequisite for us that a rack can be taken offline, but the Gluster volume still remains online. So the layout of these replicas basically supports all of the future large-scale maintenance operations that we're going to run on this Gluster volume. And the key point there is that with a good layout, we can avoid data unavailability when we take certain hosts down. And that's very important for us. So once we've created the hardware and once we've created the volume and we've handed it over to the customer, we sort of enter the maintenance phase of the volume. So one of the key steps in the maintenance phase is the hardware repair stage. So the first thing I'm going to tell you about is brick repairs. So what happens if a brick needs repair? So first of all, there's some manual effort required to do physical repairs. Let's say there's some drive failures that need to be replaced. And we do this explicitly with the local Gluster daemons on that host not running. So the partner replicas are accumulating pending heals when they're doing this. The local daemons are not running. One of the more common cases that we see is that a brick comes back completely empty. And usually this means that multiple drives were replaced in the RAID card. And in this case, we've actually added some patches to SHD to automatically discover that the brick is empty and heal it back as soon as the node is online. So there's no there's no Gluster CLI commands that are run. We just bring the heal daemon and the brick up, and it finds that the brick is empty and heals it up. The second stage that we see is root drives being replaced. So in this case, we had a root drive failure, it got replaced, and naturally it's going to come with a fresh OS. So we've built something we call the automated restore flow. So the first thing that happens is we have some global Facebook automation that installs the OS, and then Ant Farm installs Gluster. It then restores the node's prior UUID before the OS was installed, and then it restores the peer list. And so as soon as the host comes back, this process runs, and now it's again aware that it's part of a Gluster volume. And then of course, SHD will clean up all of the pending heals, or in the case that the brick is empty, we'll rebuild the entire brick from scratch. Okay, so once the other step is sort of the software side of these things. And one of the most common operations we do is push Gluster. And we actually push Gluster very often. We have almost one new build every week or 2 weeks, and we're pushing almost every week. So what are the goals for a Gluster push? The first thing is that we want to be able to push the build out quickly because we have a very large fleet. Sometimes we have hot fixes that are critical for production, and they need to be able to go out to all the Gluster volumes very fast. But at the same time, we need to be able to do this very safely. We can't have any kind of downtime when we're doing a push, which basically means we need to avoid things like quorum loss, split brains, kind of the common things you might see when you take down Gluster nodes. We also need to be able to halt the push if we find something critical. Typically for us, this means that a bunch of bricks are crashing in a volume or a bunch of NFS daemons are crashing in a volume. We need to be able to detect this and stop the push if we find this type of problem. And kind of the broad point there is that because we're pushing very quickly and we're pushing often, we have to make sure that our code changes are not resulting in any kind of incompatibility between servers and clients. So how does this upgrade automation work? So the first thing we do is we create batches of hosts based on layout. So earlier in the presentation, I mentioned that we have all of our replicas across racks. So that means that the first replica in every AFR subvolume will be in one rack, the second replica in another rack, so on and so forth. So every rack just naturally becomes what we think of as a batch. In our automation, every batch is scheduled serially. So one batch will run at a time. But within the batch, we can upgrade hosts concurrently because they're part of different replica groups. And that's how we achieve the speed that we need. So we try to decompose these type of coordinated operations into single host procedures and volume level procedures. So at a single host, we run two very important steps before installing Gluster, which is we check for quorum margin, which means that no partner nodes can be down. And if they are down, we don't upgrade the host. We also wait for pending heals to drop because anything that this node is responsible for, we want to make sure it's cleaned up before we take down the next partner. And then we follow the normal process of stopping Gluster, yum installing it, and then starting Gluster up again. When you kind of take a zoomed out view of this, the volume procedure becomes a very simple thing. We upgrade every host in the batch. We run some kind of health check to make sure that we don't have a bunch of core dumps, and this kind of can be swapped in with any other kind of health check that we want to build in the future, and then we run the next batch. And we do this until the entire upgrade process is complete. So there are a few advantages to this approach, obviously. I've mentioned that we can maintain quorum, and clients don't really know that the volume is being upgraded, so customers don't have to do anything special on their side when we're upgrading volumes. But that's not always entirely true, because it turns out that we don't actually correctly drain traffic when we stop Gluster daemons. And we are running an older build, so maybe this has changed in future versions. But at least in the build we're running, what happens is instead of not listening on the socket and then completing all the outstanding I/O, we just kind of drop the request that we've accepted on the floor. And this results in two main problems. Clients that aren't using our code, like Enfuser, end up getting some kind of connection reset. And sometimes this bubbles up to their application, and that's not a great experience. And we also end up accumulating unnecessary numbers of pending heals in this process because we have to go clean up all this I/O that we said we're going to do, but we decided we weren't going to do. And so this is definitely an improvement we can make in Gluster, and if it's there, we'd be happy to backport those patches into our build. So after we're in our steady state mode, we kind of enter the final stage. And again, this is the decommission stage. And what I mean is that we will replace 100% of the hardware in a Gluster volume. And there's kind of a bunch of challenges for this. The first is volume size. So as the size of the volume increases, as the number of both bytes and number of files is increasing, it becomes more difficult to easily and quickly replace all the hardware. And since we're moving all of this data from one set of drives to another set of drives, we have to be very careful about not losing this data, because the customer shouldn't know that we did the migration. At the same time, we shouldn't lose any of the data that they've trusted us with. And finally, we need to be within our SLA, which means we can't be throwing errors, and we still need to do this with low latency. So when we first started out with the decommission process, we took sort of the simple strategy approach, which is replace brick. So it is what it sounds like. We basically run Gluster volume replace brick on one brick in a replica group at a time. We wait for that to completely rebuild, and then we move on to the next group. It turns out this approach is actually sufficient for smaller volumes. When you have low numbers of files, this completes in a reasonable amount of time. But in a lot of cases, our volumes are larger, and we found that it would take almost a month or longer to completely move the hardware off for a Gluster volume. And this is not sustainable because we operate on much tighter timelines. And so one of the first things we did to try to improve this process, we built multi-threaded SHD. And we found that even with multi-threaded SHD, we only get so much improvement. So we realized we do need a different approach. So we sort of use this improved strategy where we are still leveraging replace brick, but we sort of warm up the destination host first. So what we do is we take the source brick offline, and we run a tool like XFS dump. Now, if you're not running XFS, you can use other tools like DD and then some kind of partition realigning if the block devices are of different sizes. But since we're running mostly XFS, we use XFS dump. So we drain the source brick over to the desk brick while the node is offline, so it's not serving any reads or writes. And then we run Gluster volume replace brick, which basically swaps in the destination brick with the source brick. So the advantages of this approach are that the first copy can be done in like hundreds of megabytes per second. It's extremely fast because we're just kind of reading sequentially and copying all the data off of the node. And then when we bring the node back after the replace brick, the self-heal daemon just has to top the node up, which basically means that it only has to heal the data that changed while that node was offline. And it turns out that this procedure is very easy to automate because it's a very fixed kind of predictable procedure that we're running. And so what we do is we've built out a kind of a larger scale automation that runs these type of individual node to node drains and then coordinates a replace brick operation. So I've just got some final thoughts on how we think about automation at Facebook. So the first is that simplicity is very important. When you're running volumes at a large scale like we are, it's very difficult to maintain if we have different kind of hardware types, if we have different volume configurations across the board. So we put a lot of effort into making sure that all of our volumes look the same across the fleet. The second thing is that layout is perhaps the most important thing we can do when we create a volume, because that kind of lays the foundation for building all of our other pieces of automation. And data unavailability is something we can absolutely avoid with a fixed layout. We try to decompose our automation into host level and volume level procedures. So we do the smallest, simplest thing we can do on a host and then build coordination logic on top of that logic. And we strive to keep the procedures as simple and predictable as possible, because overly complicated automation with a lot of different edge cases just tends to be more unreliable. And we are running a storage service, so we do have to be careful. And that's it. Thank you.
Okay. Sorry. One question for you while I go with the mic. So XFS dump you said, right? So you also have a space for taking the dump, or you transfer the data while you're taking the dump?
We basically pipe it over SSH and then run XFS restore on the other end.
Okay.
Yeah.
Do you have an opinion on how to move from Gluster 3 to Gluster 4 with this kind of automated scenario? I think you cannot afford to have a Gluster to Gluster migration.
Yeah. Well, I think that's a good question.
What would be your preferred preferred scenario?
The
for
preferred
doing this?
scenario is that we would have no breaking changes between 3 and 4, and the upgrade would be perfect. But I know that's not necessarily possible. I think what we could potentially do is do the same kind of data drains without any of the replaced bricks, and then once all of that is warmed up, we would probably just create a volume with the existing data, but it would be like a 4.0 volume. And then you could probably run some kind of parallel rsync to make sure the data is matched up, and that'd be like much easier. But that's off the top of my head, so maybe that's a better idea.
But all of this depends on having a DHT algorithm on the Gluster 4 version, right?
What do you mean?
Because you cannot update from DHT to Rio
Yeah.
fluently.
If we're changing DHT between the versions and the layouts are going to be different, then we'll probably have to actually run a parallel rsync from one volume to another. We actually have another piece of infrastructure working on to aid us with that. So I think that's probably the best option, to be honest. We have to rewrite all the data into the new volume.
Do you ever use rebalance?
We do use rebalance, yeah.
Okay, great. I'd like to hear about your experience. Maybe later there's a
Yeah,
I
yeah.
hope to have.
Yeah.
So you mentioned that you postponed the upgrade of certain volumes where they are in certain state, like healing. So when do they eventually get upgraded? You just run them in a cycle, and when they are available to that, then they just get upgraded, and that's part of the whole batch upgrade process?
That's exactly right, yeah. That's exactly what we do.
Two questions. One, when the OS drive fails, you said you have to get back the node UID. So do you back up varlib cluster D to somewhere else?
Yeah, we back up every node's UUID to like a Zookeeper-based service that we have. So every node has a property in that service that has its UUID, and then so we use that.
Nice. Second thing is about how you monitor pending self-heal. If you use the CLI to get the number of entries which are pending, to get the output of that CLI itself takes time. So are you using the same CLI or doing something else too?
No, we do something slightly different. We actually use iNotify on the actual directory that has the heals. And so we just have a service that has a counter for every create and delete entry for that directory. And so we can just look up in that service's memory, basically, like what the current pending heal count is. And that service runs locally on every host, so yeah.
Thank you. That's nice.
Steps today. Okay, so yeah, I basically have to ask, since a lot of the stuff you described is also thoughts we had and stuff we implemented in Hekedi, have you ever looked at the code base or considered it? Because, I mean, placing bricks across failure domains could be regs. We have these zones in Hekedi, it's pretty flexible. Or like replace a disk, go through all volumes that have a brick on that disk, replace it, and then replace the node. The stuff is automated there, so.
Yeah. I have not taken a look at Hekedi. The main reason is that a lot of this automation was actually built before the project was even started, because we've kind of had to be able to manage this type of thing from day one. And but if we ever do build a V2 of this automation, we'll probably go there first, and then we'll take a look at that.
That makes sense. Thanks.
Yeah.
I mean, I assume all of that is in no way out in the open. This is totally private, right?
It is totally private, but only really because it talks to like core Facebook infrastructure pieces. We've talked about seeing if we can move some of the sort of Python heavy stuff that doesn't talk to Facebook automation upstream, but we really haven't had the time to do that. But let's get Gluster upstream first, and then.
Yeah, understood. That makes sense. Thanks.
Yeah.
You mentioned about health check before proceeding to upgrade. What all things you consider in health check apart from pending heals?
We look at core dumps mainly because we've had a lot of issues with build stability in the past. Like when we roll it out, we find like crashes. Ideas can be like health checking the NFS daemons on the volume, like were they able to start correctly? Also monitoring massive regressions in latency could be something, error rates as well. Right now we just look at core dumps though, but we can expand on that.
Okay, thank you.
Thank you.